Okay, so the Henderson-Hasselbach equation. This is everything we need to know about buffers. There's not much to say about this except for we're gonna go through the math to kind of show where this comes from, and then we're gonna write out the Henderson-Hasselbach equation, and then we're gonna just briefly talk about what that means, kind of conceptually, and that'll pretty much be it. And then I'm gonna give you guys a whole bunch of worksheets to work on with buffers, and that'll be pretty much it for this week. So here we go. All right, so we've defined buffers. They're mixtures of acids and bases. And of course, anytime you have acids and bases, if you add acid and base to it, that is going to have an effect on what your acids and what happens in your solution. So we're just going to take a generic, oops, too generic here, hang on. We're going to take a generic acid-base reaction. So we have acid, and that is going to react to form H plus and the conjugate base. Right? I guess there's water on this side, but we don't include that, so it's fine. We can write out the Ka expression for this, which of course we have done a lot. H plus, conjugate base, all over the concentration of acid. Hopefully this is starting to become boring for you, and this because you understand it so well, right? That's the goal. All right, so let's say that we add, so now we've got this equation, and now we add conjugate base to our solution. So let's say that we started with, I don't know, let's say we start with a 0.25 molar solution of acid. We're going to add a solution of 0.2 molar conjugate base, right? So similar concentrations or whatever. What's going to happen to this is that this conjugate base is of course going to react with water and create OH minus. So now we're going to have OH minus on this side plus acid, and that's going to go to H plus and its conjugate base. Right? So we're just taking the same reaction, just drawing it in reverse. So the more conjugate base we have, the less H plus we have, etc. And the less H plus we have, the more it's going to change the pH. So let's take this Ka value and solve it for H plus. And why we're doing that is going to be clear in just a second. So we're going to solve this for the concentration of H plus. So I'm just going to move the acid and the base to the other side, the acid and the conjugate base to the other side, and what we get is a concentration of H plus equals Ka times the concentration of acid divided by the concentration of the base, the conjugate base. Okay. All right, so that makes sense. And this works great as long as we're really only considering the acid. Once we have the base in there, we kind of have to consider both of these things. That's when we get to a buffer. Let's take the negative log of both sides. So negative log of both sides. Negative log of H plus equals the negative log of Ka plus, sorry, my brackets got sloppy there, plus the negative log of concentration of the acid divided by the concentration of the base. Now, a couple of these terms look familiar, right? Negative log of H plus, we know that that is pH. So the pH of a solution equals the pKa, negative log of the Ka, plus, and I'm going to multiply this negative through the log. The negative log of something is just the log of the reciprocal of it. So we're going to say the pKa plus the log of the base, concentration of the base divided by the concentration of the acid. This right here is the Henderson-Hasselbach equation. And I really wish that somebody with a shorter name had discovered it. Hasselbach equation, right? Or the HH equation for short. This is the big one, right? This is always true, right? If you just add acid, of course, we're just rearranging the Ka expression to solve this, right? This is always going to be true. It's just that remember, when we have weak acids, the concentration of the of the acid is, where did my pen go? The concentration of the acid is so much larger than the concentration of the base that this term becomes this term becomes kind of not that important, right? When we have equal concentrations of base and acid, or when we have similar concentrations of base and acid, what we find is that this term changes in how it affects the overall calculation for the pH, right? So in a buffer, where we have large amounts, and again, large is a relative term, but right, when we have large amounts of both base and acid, we can use the initial concentrations, right? So 0.2 molar of the conjugate base, we can assume that the concentration of base is about 0.2 molar. 0.25 molar of the acid, we can assume that the concentration of the acid is about 0.25, right? And this is once again that cheating kind of like assumption that, well, not that much of this changes, dissociates, or anything like that. It's still a little bit of a cheat, but it works well enough for us in these situations where we don't really have to go through and use 0.25 minus X and do our ice table and figure all that stuff out, right? You can do it, you're going to get pretty much the same answer as if you don't do it. So with large amounts of both base and acid, we can use, initial concentrations. Right? So we could use 0.25 and 0.2 and plug those into over here. So that if we know the pKa of our solution, or our acid, excuse me, we can figure out the pH of our solution. All right. So this equation, which I'm going to rewrite on the next one because we're going to be referring to it quite a bit. Concentration of base over concentration of acid. Right, so this equation is then actually tells us something about how buffers behave, right? Because if we have near equal concentrations of acid and base, let's say that the base and the acid are equal to each other, the concentrations are equal, this term becomes 1, the log of 1 is 0, and the pH just equals the pKa. Right? And so what's interesting is that when we have a buffer, we talk about buffer strength. Right? Equals, and what buffer strength means is it's something that if you have a strong buffer, that means that the pH does not change much when acid or base are added. Right, and this is really useful. Actually, this is what a lot of our body chemistry is based on, right? Your blood is just a great big buffer. A lot of the stuff that a lot of the biochemical processes that work in your body are all kind of buffer chemistry, and they rely on the fact that you keep a pretty steady pH in your body, right? Because all of your enzymes and amino acids and proteins and all those things have acidic and basic functionalities on them that only work the way they're supposed to work at pH 7.4, which is the normal body pH, right? And so you need a buffer that is going to keep the pH around the same. And now we know kind of what that looks like. What makes a good strong buffer is if you change these numbers, the base or the acid a little bit, it doesn't overall affect this pH very much. So there's two things that you look for when you want a strong buffer. Strong buffers. One, you want a pH that's near the pKa of the acid. Right? So if you want a buffer that is pH 5, right, you want to choose an acid that has a pKa around 5, because what that means is the closer you are when your pH and pKa are similar to each other, that means that your concentrations of base and acid are going to be about equal. Right? And that's the second thing, is that you want the ratio of base to acid to be nearly equal. Right? This is what really makes a strong buffer. And really, these are kind of two sides of the same coin. They kind of mean the same thing. We always want, if we want a strong buffer, we want this ratio to be close to 1, which makes this term pretty close to 0, which means that our pH is very close to our pKa. Right? Now, in order to see kind of how does that make a buffer strong, how does that limit the amount of change that can occur to the pH, we need to do some calculations. And so I've given you kind of the theory behind this. The theory is that we rearrange the Ka expression to show us what affects the pH of an acid-base mixture. And then if we manipulate that acid-base mixture to a point where the acids and the bases have about equal, the acid and its conjugate base have about equal concentration, we can manipulate this into a position where the pH and the pKa are almost the same. And what we see is that that's when we get these properties of buffers, where the pH doesn't really change kind of no matter what we add to the solution. So there's a worksheet that's going to have some calculations and such on it, which will be a good thing to kind of spend some time on and kind of see how this change, the change in pH, is really hard to accomplish when you satisfy these criteria, when the pH is near pKa. All right, so definitely take a look at that worksheet. We will definitely do some of these examples in class in the meetings on Monday and Friday, and look forward to that. Okay, so that's buffers, at least an introduction to them.